Do you like books? I mean, really, really like books? Then you're in the right place. Each week, your host, Sam Hankin, interviews the best of today's top-selling authors and the up-and-coming superstars of modern literature. This is The Avid Reader. Here is your host, Sam Hankin.
Hi, everyone. Welcome to another edition of The Avid Reader, brought to you by Wellington Square Bookshop. Our guests today are Theodore P. Snow and Don Brownlee, authors of The Sixth Element, How Carbon Shapes Our World. It's published by the Princeton University Press, and it's being released the first week of June. Ted is a prominent figure in astrophysics. He's worked on Hubble and other space telescopes. His book, The Dynamic Universe, treats with astrophysical principles. He's professor emeritus at University of Colorado in Boulder and in the Center for Astrophysics and Space Astronomy. And Don, his co-author, is a professor emeritus of astronomy at the University of Washington. And he was instrumental in the NASA Stardust mission, which was so cool because it brought back pieces of a comet to Earth. You can watch one of his discussions about it on YouTube, which is really interesting. And his research covers the formation and evolution of planets and life. And he's co-authored Rare Earth and Life and Death of Planet Earth. Carbon is a paradox. It's ubiquitous in the universe, but rare on our planet, yet it forms the backbone of life, materials, and the evolution of our entire ecosphere. And as the gentlemen state in their book, everything from Ziploc bags, which they seem to like a lot, to steel, to duct tapes and tires, to the complex chains of every molecule necessary for us to breathe, sleep, drive around, fly to space, and eat our breakfast. And without it, we wouldn't be having this interview unless we lived on a world that was 1,000 degrees, had enormous pressure, and we were made of silicone, which actually may be happening in an interview on that planet about a book called The 14th Element. But carbon is also, carbon is also, although it's a cancel culture metaphor, kind of a bit of a loose woman, accepting everyone and more than willing to combine with more than one at any given moment. I asked ChatGPT if I could say that, and she goes, I call her she. She goes, yeah, it's kind of like a loose woman. So the fact that it has 4 covalent electrons to share is why we're here on Earth, and why we're here today to discuss the miracle element that gives rise to not only life, I guess, but our consciousness and our ability to discuss this very thing. So welcome, gentlemen, and thanks so much for joining us today.
Pleasure.
Great to be here.
So, I guess the way to start, would be, again, as a bookseller, to describe the way, because you guys generally deal with outer space and catching things from outer space. So describe, if you will, how this book came about, the germ of the idea, why it was a collaboration, and why, like I said, it's kind of a departure from the main path of your careers.
I'm going to start that, my guess, be a history of the book, my book, of the reading it, the book, writing a book in the first place. In the 1670s, the global warming was a big deal at that time. Carbon was the problem with carbon element was maybe attributing carbon. Carbon, the element, is cause of warning, and so I thought carbon a bad name and good reputation because carbon is the culprit, right? So we thought about the book. I thought about the book, write this years ago, but way back then. But that was maybe 40 years ago. I started thinking about it, and I had actually got John Jackson wrote the book in 2005, just before I had a stroke. And my stroke and my speaking really crummy by thinking anyway. I still wanted to get the book out at some point. So I asked John to help with writing the book with me, the book, and he was so so much agreed to do that. He must know more about some subjects anyway. So it was really good idea to him to work with me at the book. We actually John known for a long time, from the more than 50 years ago, because we were still grad school at the same time in Seattle. I know Don that long ago. They were good friends for a long time. It was nice as well, right? Really good knowledge, different places. So and the whole was a really good fit. In other words.
Okay.
Anyway, I can't say more about that. I'm sorry about my speech. Anyway, I'm here. We're there. We're ready to go. We got the book out finally. So nice to know that. So,
Yep, I agree.
thank you.
So but Don, so with regard to what Ted was saying, were you glad to be on board? Did you really like the topic to start with too?
Yeah, absolutely. Ted guaranteed me it wouldn't be too much work, which is totally incorrect. But no, I've always been fascinated by carbon. I mean, the backbone of life as we know it. And I've always been captivated by materials, and nothing is quite like carbon. It's really quite different. It's also it's the only totally political element. It has its own tax,
Yeah.
and it's amazing. You can't look at the media any day without seeing carbon, global warming. It's a huge issue for all of us. So Ted and I think that you know, everyone should know a lot about carbon because there are countries that are spending billions of dollars worrying about it. And so we wrote a book covering what we think that every single person on Earth should know about carbon. And I've personally, I think both Ted and I have always had a love affair with diamonds. We wrote a whole chapter on them, and they are quite superlative. It's different than anything else, besides being one of the rarest things on the planet.
Yeah, the thing about the book, again, we were talking before we started about the cover. And also, in addition to the cover, that it's a nice summary in the contents of each area that you're discussing, including, as you said, one that's diamonds, and which is attractive to a lot of people.
Yeah.
With regard to the cover, it is a beautiful one. And as you said, it has that matte black finish, which gives you a tactile experience. And everyone who comes into the bookstore is highly interested in covers. But what it is, it's a six-faceted diamond. And within each facet, there's a different picture photograph of something associated with carbon. So without going into too much detail about it, but again, just because this is what I do for a living, talk a little bit about the cover, how it came about, and the idea of placing these, because it's important, just as the subtitle of the book is important, to give the reader an idea, like the outside of a jigsaw puzzle box, what they were going to find inside.
Yeah, well, it certainly is a very multifaceted topic. It has so many aspects. And Princeton came up with, Ted and I both had ideas for the cover, but Princeton came up on this on their own. But a totally fascinating thing that I think that I bet most people miss by looking at it is the diamond shape on the front. So diamond is the only element in the periodic table that's water clear and transparent under room temperature conditions. And yet diamonds are famous for being colorful. If you go to the Smithsonian and look at really large diamonds, they're flashing at you. They're green, they're red, they're blue. And you move your head around and you're looking at something that's water clear. It has zero color. And why does it have zero color? Because it's kind of like glass. But the speed of light varies in diamond a lot. It's very slow. We call it a slow material. Light slows down in it. And the speed depends on the color of light. So if you cut a diamond in the shape, like on the cover of the book, it flashes all these colors on, even though it's a completely colorless material. So it's really kind of a very intriguing thing. And think of how many diamonds there are. It's one of the rarest things in the world, and yet about half the planet has a diamond ring on their finger.
The thing
One of the critics of the book, reviewing the case before he actually started writing, somebody said, "What, the whole chapter on diamonds? That's crazy. That's crazy."
Yeah.
They know better now, of course, with a really big chapter about diamonds, a good one.
Yeah, and the good thing about the book is that when you pick it up, you think, okay, this is going to be totally scientific. But not only is it, and that's still fascinating, but there's humor in it. You make interesting puns and jokes. And also, when you're talking about diamonds, you also veer from the scientific to the concept about blood diamonds, the violence associated with getting diamonds, and the social aspects of tribes fighting and things like that, which I didn't expect when I began the book. But I really like that you go off on these tangents about, just like you're talking about climate change.
Yeah, we also in the book, because I mean we are both scientists, and we love science, but we didn't want the book to read like a chemistry book.
Right.
And so
Well,
we tried to add things to it. And one thing we added, we were looking at the whole subject of carbon through a lens of history, which we got into issues with, because we had to deal with some history reviewers, and that is very interesting, because you and I know all about history, right? But historians know more than we do. And they know that such and such was just proven, 2.5 years ago, and we didn't hear about it. So anyway, we had a lot of reviews of this book, but the history reviews I thought were the most interesting, and the real historians view the world differently than most of us that live on the planet.
Yeah, and not being a scientist, I was thinking there are formulas in the book. But the thing about it is, and I don't know why, but they were more accessible than normally when I see it in a book and just gloss over them. Specifically, the first one, which was caffeine. And you talk about being perky and all that.
Yeah.
We don't have the I don't have the galley in front of me because it's electronic, but that diagram of caffeine was fascinating because you could actually look at it and you could go, I had like an aha moment where I could actually see, because I was horrible at chemistry, but I can actually see, okay, I can get this idea.
Yeah.
That was fun.
Yeah, so you included formulas, but they were much more accessible because you surround the formulas with the words that describe how these things, and again, it's because it's carbon and talk about that. And you can also bring in silicon, because I jokingly talked about silicon, but talk about why carbon is the very reason why we're here, and why, because of its electron shell, we're able to live.
Well, carbon is truly the Swiss Army knife of the periodic table. I mean, it really is. I mean, there are, many elements can form different compounds. Carbon can form an infinite number of compounds, and it can bond to almost everything. And for life, I think it's fascinating that we rely on very complex molecules that can contain tens of thousands of atoms. And these molecules didn't pop out of thin air. They had to be developed and refined. They have cross branches, and they're very complicated. And some of them took millions of years to evolve. I mean, one of the key molecules that's responsible for photosynthesis evolved before there was free oxygen in our atmosphere 2.5 billion years ago. It started evolving, and so it's really quite amazing. So you mentioned silicon, and I laughed earlier in the program when you mentioned silicon, because who knows about life in the universe? Is there a silicon-based life? But most people, you say silicon-based life, they'll raise their eyebrows and think, yeah, that's a good idea. And yet I don't know any actual astrobiologist, molecular chemist that believes it's possible.
Yeah.
And one reason not for believing it, well, I mean, there are arguments, things like, CO2 is a gas, so we can exhale CO2. If we were based on silicon and we oxidize silicon to make silicon dioxide, it's a solid. You can't exhale quartz, out in the air. But also, just think of it. On the early solar system, we had an infinite number of environments that had carbon and silicon, water, warmth, and so forth. I mean, we have 100,000 meteorites that are samples of asteroids, which were warm and wet for millions of years in the early solar system because they were heated by the radioactive decay of an isotope called aluminum-26. And so you had the perfect setup for silicon-based life, and no one's ever found any evidence that there is silicon-based life. So it didn't happen here.
Right.
And other places are more like here than they're not. So I take a dim view of it, and most astrobiologists do, but that doesn't mean that we're wrong. We're not wrong, but there's always the possibility. But we've been to Mars, we've been to the moon, we've looked at thousands and thousands of meteorites, we've looked at comet samples and asteroid samples. No silicon-based life.
We're all contemporaries kind of in age. And so we've all read the same books, Heinlein,
Yeah.
Ray Bradbury, Theodore,
Right.
Arthur C. Clarke. And you talk about those guys, which just always makes me happy. But I was thinking about, nanotubes and the space elevator and fountains of paradise. And then I was thinking about the Martian Chronicles, which you bring up as well. And then the one that really intersects in this book is Fred Hoyle, because I read The Black Cloud,
Yeah.
and the Big Bang is his joking name for something that we now
Right.
accept.
Yeah.
And the thing about it is that, which then brought me to something that made me think a lot in the book, is the anthropic principle.
Right.
Yeah.
And you talk about it too, and it's like, okay, yeah, all this stuff about carbon, well, that's why we're here to talk about carbon.
That's right.
We wouldn't be here.
Yeah.
And the anthropic principle has always gotten me, because even if you go to and you also talk about Drake's equation. And so but I keep thinking to myself, well, we just happen to be very, very lucky, and in the Goldilocks zone, which you talk about as well. So what do you guys really think about that? Because you do bring it up early on in the book.
Yeah. Can I talk about that? Or so Fred was a real character. And he was also robbed for not getting a Nobel Prize for what he did. He should have. But he didn't, part of it because he was such a character, but because he did brilliant things, but he was also very stubborn on things. Like, he also thought diseases came from space. But the anthropic principle was an amazing thing. So in the early universe, when you're making elements, the carbon was a barrier. It was a barrier to producing heavy elements. So you have nuclear reactions, and you take two helium nuclei and collide them, and you form an isotope of beryllium that has called beryllium-8, which has an incredibly short half-life, less than 1 femtosecond, 10 to the minus 15 seconds, less than that. And there is a way around that, is to hit it with another helium nucleus, and you form carbon-12. But the carbon-12 isotope has too much energy, and it instantly falls apart. And so Hoyle looked at this and he said, well, there's got to be some magic state there, which there is, and it's now called the Hoyle state, that allows the excited carbon that forms to settle down a little bit and occasionally to survive. So it's a way to make carbon. It didn't happen in the beginning of the universe, but it happens in massive stars later on. So he predicted this just because we are here, the anthropic principle. If we weren't, if this didn't happen, carbon wouldn't have been made, and we couldn't possibly be here. We would have an entire universe made out of hydrogen and helium and a little bit of lithium and beryllium, and which is kind of a dreadful thing to think of a universe. But nature found this way, and the path was the Hoyle state, which is still a little bit mysterious to physicists, but he did this work, and it was fantastic.
Yeah.
Well, are we old enough for us to have met Fred Hoyle? Did you guys know him?
Yeah,
No.
I know him. Yeah.
I didn't meet him, never, I didn't know him, but he was around, still alive when I saw him. I know what I know we have. I know his faults is also is brilliant as well. It's fun to see about him.
Huh. The other thing you just mentioned, carbon-12, and I tend to jump around, but everything you say gives me an idea about something in the book, and that's another reason why the book is so good, because you can close the book at the end and you're still interested, and you start studying other aspects of it because you gave me an idea. Like, so one is carbon-14, and maybe most people, I don't know, maybe most people do know about radioactive dating, but you devote a good portion of it, some portion of the book, to carbon-14. So for those who don't understand how that works, maybe you could explain why carbon, again, of all things, why carbon is able to allow us to determine how old something in our world and the universe is.
Well, carbon-14 is this phenomenal gift to us. Almost all carbon is called carbon-12. And there's another stable isotope called carbon-13. Carbon-14 is radioactive, and it was first discovered at Berkeley back in the 40s, and it was first found in nature in Baltimore. Sewage, collected sewage from Baltimore, and they could count it, and because it's radioactive, and they could count the decay of it. Anyway, it has a half-life of about 5,000 years, and we now have incredibly sensitive ways of measuring it using special high voltage mass spectrometers, and you can measure this radioactive isotope in extremely small, being like little grains of wheat and so forth. But the thing about carbon-14, it's made in the atmosphere by cosmic rays hitting nitrogen in the atmosphere. So it's continuously produced. And then the carbon-14 goes into making plants. And so vegetarians eat the plants, and some non-vegetarians eat, like lions get carbon-14 in them, not because they eat plants, but they eat animals that eat plants. They devour vegetarians. So anyway, living things are intaking carbon-14 from the air. And so when they die, this carbon-14 decays. And it's kind of interesting. So it's the time scale of the decay is like the time scale of known human history. So we have this fabulous technique to be able to date things. And this was actually calibrated. It's fascinating. Originally, it was calibrated by dating things that could be known, such as the age of pyramids and Egyptian artifacts, and also tree rings. But now it's a fantastic thing. So there are, I don't know how many carbon-14 dates there are made per year, but it's a huge industry, because people that need to know the date of something can take their sample and send it off to some place, and they'll measure the carbon-14 age. And so it has to be corrected for various things like the flux of cosmic rays varies, and also uh, World War II and the post-war. We did all this nuclear testing after World War II, and this released all man-made carbon-14 into the air. So there's this thing called the bomb spike. The carbon-14 in our atmosphere increased because of atmospheric nuclear testing, which fortunately ended when I was like in high school. I think they had the last nuclear test in the atmosphere. But this bomb spike from nuclear testing was fascinating because people could look at the extra carbon-14 put in the atmosphere from nuclear testing and see how it decayed with time. And it didn't decay because it was radioactively decayed because the carbon dioxide, which we're all terrified of and worrying about every day, went into the ocean. And it took it took till the present time, from the 1950s to the present time, for the bulk of that carbon-14 from nuclear tests, to go back, dissolve in the ocean. So that was one of the first findings that we were going to be in trouble about injecting carbon dioxide in the atmosphere, because some people thought that the ocean would be able to soak this up very quickly, but no, it took over 60 years to do.
Yeah, that's one of the things that you talk about, and I think you do describe the exigencies of the possibility, the likelihood, the fact that climate change is occurring, and the consequences of that, and the fact that we're not really going to slow down in our use of fossil fuels, at least in the near future. And that spells not doom, but a change in our world that's similar to the geological changes that have taken place over time. But you point out the paradox is that we need carbon. It's totally important. It's something that we have to have, yet at the same time, it has this downside, and you kind of give a balance of that. So yeah, I mean, it's not a kind of thing that we should be afraid of generally, because it is why we're here, and you kind of balance those two.
Yeah, well, we are afraid of it because we can't. Planets are very complicated, and there are many interacting systems, and so ocean circulation, ice pack in the polar regions. No one really precisely knows how to predict that. However, to me, I mean, as a scientist, people, when I say, well, when I read that the world is going to end blah blah in 30 years, but because of this, I think, well, that's ridiculous, because the Earth has been here for 4.5 billion years and seen a lot of stuff. However, we have perturbed the atmosphere. There's no doubt about that. There's this famous Keeling curve, which is a measurement of carbon dioxide on Mauna Loa in Hawaii. It's a continual increase, and it's doubled. The CO2 has doubled from the time from the first humans were on the Earth. It was about 200 parts per million. Now it's 400 parts per million, and so this will have unknown consequences. It will not destroy the Earth. It won't destroy all life on Earth, but it certainly affects us and our civilization and our crops and how people deal with sea level rise and so forth. So it is a huge concern, and it's every country in the world is spending a whole lot of money trying to adjust to this. So it is a really big problem. That's why everybody should know all they can about carbon,
Right.
both its good parts and its bad parts.
Yeah, you even have a chart showing the sources of power. Yeah, the charts are really good too, by the way, and the footnotes too. But you have a chart showing, 30% nuclear power, then the renewables, and then the petroleum. So it gives you a really good idea, but a visual idea. And you talk about, like France has what, 70% of its power is from nuclear power.
Yeah.
And to me, as a layman, I've always thought, well, yeah, you talk about Japan and Chernobyl, but at the same time, yeah, I look at it as, but the risk is small, but the consequences are disastrous. So, and it's also incredibly expensive to build nuclear power plants and takes a long time. But it always seemed to me like that would be the simplest way out. And then you also talk about fusion, which is, pie in the sky.
Right.
Yeah, it's a complete unknown, and the irony is, we would be nowhere without the black burnable rocks and gas and oil. The whole rise of humans above all other animals on the planet are because nature made this fossil fuel for us. So it enabled us to be what we are. And now we've gotten ourselves into a real pickle. People can debate whether it's real or not, but it is real. I mean, it's not gonna kill us all, but it's causing us. There's no doubt it's causing us problems. So it's totally
Yeah.
fascinating subject as far as I'm concerned. I don't know. So
Well, that's, bringing up petroleum, that leads to the more than one chapter, but it's kind of funny. Which I don't know which one of you is the more whimsical in the manner in which you present the book, but one of you has a really good sense of humor, or both of you do. When you talk about duct tape and then cellophane tape, Scotch tape, Velcro, what else? Post-its, and you realize everything is because of fossil fuels, and you can't be a fossil fuel denier because that's where every single thing came from. And just that section, that paragraph, maybe just describing tape, gives you an idea.
yeah,
Or Ziploc bags, polypropylene.
yeah.
So
Plastic, just plastic in general is carbon based.
Oh, and then you talk about Bakelite and the smell.
Yeah.
And I remember when, Christmas morning, we had our Lionel trains. I remember that transformer that had the little, and that smell was like, I can see it now in my head. It's so evocative.
Yeah, it's funny. That's a smell that's disappeared from our lives.
Yeah.
But above Lionel trains, airplanes have the same smell, and also Army surplus stores, when they used to have Army surplus stores.
Yeah, I remember those.
That smell.
Yeah, right.
And I wrote the thing about the B-17 because I was down at Boeing Field and stuck my head in a B-17, and boy, you could smell that formaldehyde smell inside.
Yeah. I used to love when my dad would take me to the Army Navy store.
Yeah.
Oh, yeah.
On Saturday. You find some weird things there.
Yeah.
Nothing you really needed, but you bought it anyway.
Yeah, well, we always like when I was in high school, I was always involved in building weird things, things usually made sparks or explosions or something. So we always went to the surplus stores, and you could find some amazing things. I mean, we bought a lot of radar jammers, which you could get for like $1, and those produced high, like 40,000 volts. We to do, and we had one that had a explosively actuated parachute in it, which we didn't know about, and it blew this parachute across the room. It's
Well, it's like
these things they drop from airplanes. So anyway.
Some of this stuff is like no one's going to remember but me and everybody else my age. Is like what you were saying. Can you imagine trying to sell a chemistry kit like we used to buy?
Yeah.
Right.
OSHA and the Consumer Protection Agency would put you in jail.
Right. Right. Not allowed now.
We blew up a lot of stuff.
Yeah. Yeah. We all did our age. Yeah.
Yeah, I remember in our basement, we burned up a bunch of stuff burned up my father's workbench, and he came down and goes, what the hell is this? And there was this big black crater in the middle of it. I forgot what we mixed together.
Yeah, no, I think at least half of my interest in science came from powdered magnesium in chemistry sets.
Magnesium, yeah.
Powdered magnesium. I mean, they all the chemistry sets used to have powdered magnesium in, and so it's very easy to make flash powder. I never saw it, but they also had nuclear chemistry sets, and it's you can look it up on the web, and it's kind of interesting stuff. And
The worst thing was that my uncle, who was a dentist, gave us this big vial of mercury, and my brothers and I would play with it and put it in our hands. We put it in the freezer to see if we could freeze it, and then we take it out, and we wouldn't wash our hands and put our fingers to our mouth. It's in here somewhere.
Right.
It didn't.
well, yeah, I mean, it was a standard thing to take quarters and dimes and clean them up with mercury, because of the surface of it. Yeah,
that and put them on railroad tracks.
yeah.
We all did the same things.
Yeah,
Our age, yes.
That's so funny. Well, switching from the chauvinistic aspect of it, the other good thing about the book is you bring up the women who were involved in all this stuff, especially like with Crick and Watson. But then I never heard of this woman, Mary Leah Hagel, and the mystery bands, which sounds like trivia night at a bar, mystery bands. But talk about her a little bit, because she deserves to be talked about.
Well, my part of the book was the use bands. My topic, my research topic for me is, I know what there's a girl, Theodore, and she first found out these bands, the booze. Jesus, I'm sorry, but anyway,
Sorry.
as a grad student, you found out these spectral lines for the dibs. They're called blues bands at that time. She noted them, and then noted them, and that's it. There's not anymore. She went to a grad school as the wife of the other scientists. No research anymore. But the fused bands made a big deal. After all, the fused bands have maybe 20% of the carbon in the universe. Use these bands, we don't know what it is. So matter doing molecule, know that or molecule base. We don't want molecule to do it. We have ideas. We don't know. Maybe ever to find out. There's so many different possibilities for the fused bands. Maybe never know exactly which molecule to cause them. That's fun. My research myself. My thesis research project was the fused bands. So that's still learn about the fused bands even now. So a big topic for me all life from my life. So it's neat. I love it. That woman, the woman who started this whole thing more than 10 years ago, still be a little bit debt for thinking about that in the first place, I think.
Yeah, it was really nice that you give her it's really nice that you gave her credit, because I think that's so important, because people always forget that it was the women behind the men that did a lot of the dirty work.
Yeah.
Brings me to, like, I mean, if we're going out into space, you devote a whole, I don't know if it's a whole chapter, maybe. Yeah, but you talk about exoplanets, and then again you do a great chart showing the Earth-like rocky planets, and then the super Earths, and then back out to the gas giants. And that chart, I think, is fascinating. And yeah, who did the charts, or did you borrow them? Or
NASA did that one.
okay. Oh yeah, that's right. That's right. You give the, yeah, I saw the credit on it. So what about that? Talk a little bit about exoplanets.
Well, who knows? We know they're there now. We know that now. Years ago, there's no extra planet at all. We didn't think about that there at all. But now we know it's really common now. The Earth-like planets not so much now. So Earth-like planets are not with long far away from the suns, hard to find because they only have long lifetime of the years. They don't long the years. So finding those planets from Earth-like planets are hard to find because they have long lives, years and years and so on. So hard to, and also they so a little massive or size, they're hard to see. So we know they're there. We don't know what they are. We don't know how their carbon base and so on, life and so on. We don't know. We think we must be there, but we can't see it so far.
Yeah, and that reminds me, Dan, of what I mentioned in the introduction about Drake's equation. And in my lifetime, I never thought we'd actually solve the first factor. And I never thought about it until you guys said it. So yeah, Dan, talk about, some people may know about the equation, whether there's life in the universe, but talk about those factors and how we, because of our equipment now, can actually just cross off the first factor.
Okay.
Well, Don, take that with, please.
Okay. Well, I'm a little bit biased because I'm a co-author of this book called Rare Earth, but no, the Drake equation was a way to estimate the number of communicable civilizations in the galaxy that you might be able to communicate with. But anyway, it has a whole bunch of factors that you multiply times each other. And a factor can be 1, 2, a small number. And one of them was what fraction of stars have planets. And some people thought, well, the sun was a real fluke having planets. Most stars don't have planets. Well, it turned out that was completely wrong. We now know that almost all stars have planets, and the planets form naturally when the stars form. However, don't expect that this process leads naturally to Earth, because most stars are not like the sun. Most typical stars are less massive than the sun, which has some good and bad aspects to it. One is that if you want to have an Earth-like planet in the so-called habitable zone, which is the range of distances from the star where you can have surface conditions to have liquid water survive, like a surface ocean, then for a less massive star is much fainter, and so you have to get really close. And in fact, so close that the planets tend to tidally lock. Like, our moon is tidally locked on Earth because it's so close to Earth, which means it always had the same face of the moon facing the Earth. Well, if Earth was orbiting a very low mass star and it was close enough to be warm enough to have oceans, we would be tidally locked. So half of the Earth would always face the sun, and the other half would always face away to the dark. So anyway, so stars are different, and the sun is not a typical star, even though it's commonly said that. And the Earth is definitely not a typical planet, even though people imagine, well, most planets are going to be like Earth. Well, they're not. Most planets are gaseous planets, And the most common kind of planet is actually what's called a super Earth, which is kind of like Earth, but more massive. And sometimes with extended hydrogen atmosphere. So from the fantastic discovery of thousands of exoplanets orbiting the stars, we see that there's a huge range of kinds of planets that form. And no one is that, even though you hear the word Earth-like a lot with exoplanets, none of them are really known to be Earth-like. And to me, Earth-like means if you were there, you would feel at home. You, you could breathe the air and look out and not freeze and not burn yourself up and so forth. So in our solar system, there is no other place that's remotely like Earth, even though some people talk about like Mars being Earth-like. Well, it's not. And you can be sure that Elon Musk is going to be very bored once he gets to Mars. The third month, he's probably going to go nuts when I come home. But because it's Mars, it's not Earth. It's a totally different planet.
And
Anyway.
see, again, like the things you just talked about, and the reason why I'm looking down is because I'm writing notes because I'll forget it because I'm old. A couple of things you talked about. You talked about surfaces, and I never thought about surfaces. And you talk about planets that don't have surfaces, and I realized, oh, you need something, a floor. And then I thought about not carbon, but water. And you talked about solvent, and then you talked about silicone, how it wouldn't work with water and then so all these things start going around in my head. And then you do talk about Titan and the fact that it has lakes of hydrocarbon. And then I started to imagine that. And it seemed that as if you were suggesting, okay, this could be a harbor, no pun intended, for a certain type of life.
Well, yeah, Titan is often called Earth-like, but it's 90 degrees. 90 degrees absolute, so it's colder than liquid nitrogen. So nothing on Earth can live on Titan, on the surface.
Right.
But all these cold bodies like in the solar system further away, they're cold on the surface, but they get warmer as you go in. So below the surface, there's some level where you have sort of room temperature kind of conditions where you could have liquid water. But that's a totally different, we have subterranean microbes on Earth, but nothing at great depth. So I don't know. It's just an unknown. I mean, it's a very exciting time because for the first time in history, we're learning a lot about the diversity of potential places where life might exist and can exist. And when we say habitable planets, a habitable planet is a planet where life as we know it on Earth might be able to exist.
Yeah, you talk about extremophiles, and so then I was thinking about tardigrades, and then I was thinking about, I guess, what might be a myth that the Chinese lunar lander might have tardigrades on it. It's like, so tardigrades can, what's so impossible, impracticable about the idea of something like a tardigrade living somewhere in the interior of Titan, or even Mars?
Well, we just don't know, but life on chemistry, life based on carbon chemistry, it only works in a certain temperature range.
Yeah.
And even the extremophiles, I mean, on Earth, there are things that can live in boiling water and live in frozen ice and so forth. But there's nothing that can flourish in those environments. And those are also microbes too, which are very much different than we are. And so there is no great organism that can jump from one to the other. There are things that have evolved to adapt to be able to survive under those conditions. Like we got feedback on the review about, we talked about the dinosaurs. Sure, they lived on Earth when it was a lot hotter than it is now, and the CO2 was much higher, and so forth. And the experts said, yeah, but that's because they evolved to live in that environment. You know, it was 100 million years ago, and things were different. They weren't horribly different. They weren't at all like Titan, but you know, we would not be thrilled to be in living in the dinosaur world, because the conditions were just different. But they evolved. So biological evolution can adapt, can make things that live in extreme conditions, but there are limits to how extreme. And on Earth, you know, the environments go down to a few kilometers and up a little bit above the surface, and that's it. And so when people say Earth is teeming with life, well, it's only this little band where the conditions are right. You know, there's nothing in the core, nothing in the mantle, and nothing really high altitude. I mean, you know, this comes up. People say, well, Venus could be a great place for Earth. I mean, great place for life, but they have to be floating in the clouds. Well, you know, sure, maybe that's possible, but maybe it's impossible. More likely, it's impossible. But
Remember that? Remember Ray Bradbury's story, The Sound of Thunder? I guess it was called, when the guy goes back in time and has to go on the walkway, and then he steps on the butterfly. You remember that?
no,
He steps on the butt. He's in the present, and there's a really nice president. And then he goes back, and he's a coward, and he jumps off the path, and he steps on a butterfly. So it's the butterfly effect that changes everything. And then he comes back, and the president's someone like Trump.
no, I see.
That was a good story. Yeah. So you guys, when you were little, you were talking about, you know, causing explosions and all. So what was it for both of you that got you into? You talked about your thesis, Ted. But okay, what was it that got you from? I was playing with magnesium ribbons. I love the ribbons, lighting them. It was so bright. My brother and I, it's amazing I'm still alive. But yeah, what was it that got you from that point as kids, you know, doing what we did and your hobbies into your various specialties?
Well,
Was it a moment?
I have to, having a set, boom things on. Everyone does, our age does. So I have some science all the way through. I know when the scientists are either that or a mathematician. When I went to college, what is really happening. So I math is out for me, boom, right away. So stuff with science and something on the side of the other. So I happened to go to astronomy course, really good astronomy course I took. First science I had was astronomy. That's it. So I went to I have the astronomy and physics is high school, and then in Seattle, grad school with Don as well. Science went to the astronomy department, my PhD. Then as the guy who my supervisor told me about PhDs. I said, "Oh, that's interesting." He had some spectra to work on, and I know about dibs and the dibs that point in high school and in grad school. When my first job was in Princeton, had to be a colleague with me, also working on dibs, whose band as well. My path was already set. And my main thesis, research thesis project for the role of my career was dibs. A lot of things, other things are divided, but the dibs are my main project in my career was dips.
It's funny how you have a passion, you know, and then that passion stays with you for your entire life. So
Well,
what was yours, Dan?
Uh, I don't know. I always had an intense interest in science and space, and it just naturally evolved. When I got in graduate school, I was very interested in space, and I got I was very lucky to have uh, access to space. I got to put collectors on the Gemini spacecraft, and
Oh,
that was a real thrill.
amazing.
So Ted and I also have an interesting graduate student story. You talk about women, and we talked about several women in the book, and one of them was Cecilia Payne Gaposchkin, uh, was her final name, and she was the one in 1925 that first discovered that the sun was not made out of earthly elements. You know, when spectroscopy first was used on stars, you look at the spectrum of the sun, and most of the spectral lines you see in the sun are iron lines, or earthly like things. So she did a thesis, and she was actually the first PhD uh, in America for a woman in astronomy, and she tried to go to school in England where she grew up, and they would not allow her to enter graduate school, so she had to go to Harvard. And anyway, but her thesis was figuring out this thing about the sun, and she discovered that the sun was made out of hydrogen and helium, and not iron, magnesium, silicon. I mean, it contained those things, but they were very, very minor elements compared to hydrogen. And this was one of the greatest discoveries in astronomy, and it was done by a woman. That was a really that changed everything, because you know, once you know that the universe is made out of hydrogen and helium, you wonder, well, how did that happen? And so that opened the door to all of our understanding of how the elements formed, including carbon, and the whole and the Hoyle's level and all the stuff. So it really opened doors, but it was also intriguing that uh, her graduate student was at Harvard was Paul Hodge, and so she was his advisor, and Paul was my advisor here at the University of Washington, and before that even at Berkeley, and she also gave thesis advice to a young Harvard grad student named Jesse Greenstein, who became the graduate advisor of George Wallerstein at Caltech, uh, who was Ted's thesis advisor at the University of Washington. So it's really intriguing when we're writing this book. I think neither of us could have really realized this linkage, but it was a direct linkage back to Cecilia Payne Gaposchkin in 1925.
Yeah, it's like a family tree. You can draw it out.
Yeah, yeah.
And she's in the most poignant photograph of the book, right? She's in that dramatic picture with women. She's the
Yeah,
first.
that picture was taken on the last day of 1929, you know. So, I mean, talk about a time in history, you know. The
Yeah.
depression was falling on them. Yeah, almost all the people in that picture ended up being very famous, but they weren't famous at the time. I mean, the most of those women in there were the famous Harvard computers, and I believe they made 25 cents an hour.
I took, since I had it on my computer, I enjoyed zooming in on the women's faces and looking at their various expressions. Such a cute picture.
Yeah, I have I just happened to have this on my desk, this is a play.
Yeah.
It's called Silent Sky, and it was about these women.
Oh,
And
wow.
it circulated around the country. It's,
I'll have to get that.
yeah.
Well, you know, so as we wind down, there was one topic, and then I'll let you guys go. And you talk about it throughout the book, and it's, again, one of the esoteric things that carbon can do, and it's single-walled. And it reminded me of Fountains of Paradise because of Arthur C. Clarke and the idea of a space elevator and geosynchronous orbit around the Earth. And I thought about nanotubes, and I was going to ask you, because every time I say something can happen, you kind of knock it down, Dan.
Oh, I don't know. I don't mean to. Sorry.
So, is there a possibility of a space elevator using nanotubes? You're just gonna say no.
No, I have to say yes. 2 days ago, I read that the Japanese supposedly are working on a space elevator,
Really?
and there's a company there, and I think they gave a target date of like 2050. But it's a question: can you make something strong enough to 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 do it? And it would be something like carbon nanotube. Um, in case anyone doesn't know what a carbon nanotube is, it's chicken wire rolled up into a straw.
That was a good
made out of carbon.
Well, the other thing is that the picture of the buckyballs with the soccer ball. That was really good. That's a good way of explaining them.
Right.
And then the fact that science imitated art in the sense that Buckminster Fuller created those before we knew they actually existed.
Right.
Yeah. Well, there is an astronomy connection to that in like in Ted's field is the strongest featured. Ted had a plot in there. The strongest spectral feature in the ultraviolet is this 2200 angstrom feature, and Harry Kroto in England thought that might be due to some spherical carbon molecule, which then later was discovered, and it was it's interesting because he got the idea for it, and then people said, well, yeah, but nature would never make something like that, and it turns out it does. I mean, even candles make C60 Buckminster fullerenes. But there was a direct link to astronomy and also the industrial production of buckyballs also has a direct link to astronomers, which is kind of interesting because
how soon do you think it'll be that nanofibers, nanotubes are actually going to be, or are they really being used now in practical applications? And I mean, you talk about how carbon fiber is now used in everything from airplanes to bulletproof vests. So how
submarines?
Right.
We missed the part about the submarines.
Oh yeah, go ahead and tell that story.
Well, no. Well, the implosion of the submarine, the Titanic.
Yep.
That's a carbon fiber based thing.
Well, yeah, but he was using a Nintendo controller.
Yeah. But anyway, yeah, it's
that should never have happened. That was a real tragedy.
Yeah. I don't know. It's interesting. You can draw an analogy to lasers. So lasers came out in the 60s, I think, invented, and then there were some lasers, but hardly ever, and now everyone owns lasers.
Yeah.
and there's an uncountable number of lasers in the world. I think it just takes time, and who knows? I mean, Well, what was it? Some of these new carbon forms, may be used for, purifying water and cleaning beer up and making fresh water from salt water, which is a huge deal. And who knows? Sometimes these things work, and sometimes these things don't. I mean, like room temperature superconductors have, are incredible, but haven't affected any of us so far. I think, so.
And the idea of room temperature nuclear fusion, and
Yeah, yeah.
Well, anyway, so I could go on forever with these questions. I was fascinated with the book, and like I said, us being contemporaries, we could go over memories we have of stupid things we did when we were little. But I want to thank both of you for taking the time to talk to me. Ted, I understood everything you said, so don't worry about that.
Thank you for saying that.
Yeah, no, I did perfectly, and it was all fascinating. So thank you both for doing this. And as I said, being the bookseller I am, I will come out from behind the counter and hand this book to people and say, "Hey, you have to read this."
Great. Thank you.
Okay.
Thank you.
Right. Thank you. Bye-bye.
Great job.
Thank you.
Bye. Bye.